Okay, folks, let's maybe continue. And as a starting point to the next part of today's lesson, maybe I'll ask you, now that you had a little bit of time to think about what we were talking about in the first half of today's lesson, do you have any questions about anything we've seen so far with reading in data files or the basic kind of data manipulation stuff we've been doing with pandas at this point? Any issues or questions or concerns? Okay, well, if not, that's not a problem. We are going to leave our exploring data using pandas notebook behind at this point and jump over to the other notebook for today's lesson, which is something like processing data in pandas. I can only see a few characters of the file name here, but if you start by just double-clicking on that notebook to open it up, you'll see, yes, indeed, it is called Processing Data with Pandas, and that's what we will continue with for the rest of the lesson part of today. As we did before, we're going to start things off because we're in a new notebook. We need to import pandas again, so we'll just do Shift-Enter on the first cell. You don't have to type anything in this instance to get pandas imported. And then we're going to read in our data file, and this time we're going to do it a little bit more like what you would typically do when you're working with data files in Python, and that is to define a file path and then read in our data file from that file path. So we could say, for instance, file path is often abbreviated as FP. And then in quotation marks here, we'll give the name of our data file. I'm just going to type Kumpula and hit tab because pandas will, or sort of Python will recognize that we're trying to use a file name here. So this is the name of our data file. And often when you read in your files, you would define a variable called FP first and then read it in so that if you want to change things, it's easier to modify the value of FP than it is to modify it in the way that the text is being read, or the file is being read in. But we'll basically do the same thing we did before and say data equals pd.readcsv underscore CSV. But instead of putting our file name in quotation marks here, we can just list the name of the variable FP. Because FP contains this character string, we don't need to type that in. So it makes things a little bit shorter to look at that line to see what's happening. But of course, we also still need to include our skip rows equals 8 parameter because we still want to skip the first 8 rows of the data file. So slightly different format for how to do things, but if you run this cell, you should end up with the same result, and we can check that by just doing data.head in this notebook. And you'll see if you do data.head, the same data that we were working with in the previous example from the first notebook we were dealing with today. So why would you want to do things this way? Why would you want to label the file path with this variable FP first and then read it in like this? Well, part of the reason is that depending on where your code is, what kind of operating system or how you're using pandas or anything in Python that's reading in files, you can provide either a relative file path, which is basically the location of a file relative to where you are in the file system currently. So in our case, we are in the same directory we're working in with these notebooks. We have this text file called Kumpula June 2016 with metadata. This we can then supply as a file path without needing to provide anything about like a directory where the file is located or anything because it's in the same directory as our notebook. So when we define our file path up here, we just said FP equals this. Now, what happens if we move this notebook to a different directory? Well, this won't work anymore because it's going to then, if we don't move the data file, we're going to have to add something to identify where this data file is stored. So as an alternative to the relative file path, which we've given earlier, You could list the absolute file path, which is a little bit longer, as you can see here. But this gives the location of the file relative to the root or the base of the file system. So if we were to look around and play around in this Jupyter Notebook environment, we would see that the directory where everything starts is from this root directory with this slash, and then inside there's a directory called home. And inside home, there's a directory called Jovian, which is the sort of name that's given for Jupyter Notebooks. I don't remember what the story is here, but it's like, or maybe it could be something to do with the cloud computing environment, but this name is always there. Then you have your My Work folder, and inside My Work we have notebooks, and then inside notebooks we have L5, and then finally we would have the name of the file that we're working with. The benefit here is that if you give the absolute file path, it doesn't matter where you put the notebook, because you can move the notebook around and then it can always find the location of the data file that you're working with. So typically when you give this long absolute file path, it's nicer to define that as a separate variable. For example, FP, like we did up here, instead of putting that into the pandas.readcsv as this very long character string. So that's the reason, or one of the reasons why typically we do things this way when dealing with data files. I myself typically will put this sort of absolute file path just because I do move code around on my computer and I don't want it to break just because it can't find a file. So if you give the absolute file path, then that's one way to make sure that if the source code moves somewhere else or if the notebook moves somewhere else, that everything still works. And then there's an example here of how to give the file path as what's called a raw string. So this will avoid problems like if you have a space in the name of a file or things like that. Putting the R in front of the quotation marks will treat it as a raw character string. So yeah, that's just kind of a little side note. But we've got our data file now, and let's do some stuff with this data frame. We can start by creating a new column in our data frame called diff. And so what we can do is say something like data, then we put square brackets, and the new column name is diff equals 0.0. What we can do with this diff column, we'll see in just a moment, but we could, for example, store the difference in temperature between the maximum and minimum for the day. But whatever, we're just going to, for right now, set the whole column to be equal to 0, and then we can do data.head to see what changed in our data frame. So data diff equals 0, data.head, and that will let us define a new column and see what happened. And so as expected here, you can see now we have 5 columns in the data frame, and the 5th column has been named diff and has all values of 0 in that column. If we check the data type of our new column, we can do that easily with the type function. And we could do data diff, right? Like that, and another close parentheses. And we could do that way. Actually, that's not what I meant to do, because that'll just tell us that that's a pandas series. What we actually want to do is .dtypes. So we did this to look at the data type of all of the columns of a data frame, but you can also do it to a single column, just adding this .dtypes. And you can see here that we have 64-bit floating point numbers in our column, and that seems to make sense. We have numerical values there. If we, for instance, were defining this as not 0.0, but just as a value of 0 with no decimal place, you would see then when we check the data type that it comes back as an integer with 64-bit precision. So when you define this value initially, if you include the decimal place, it will see it as a floating point number. If you don't put a decimal place, it will treat it as an integer value. So what we did was like this, and because we put the decimal point in here, then when we check the data type for that column, you can see it's a floating point number. No big surprises there. Okay, so we've set this value to be 0 to begin with, and so we can update our value that's in our new column by doing data diff equals, and then we can subtract the minimum temperature for the day from the maximum temperature. So that'll give us a sense of how much did the temperature vary in a given day. So if we say, for instance, data max minus data min, that will now fill in the values of our data, or our diff column rather, with the difference between the maximum and minimum temperature for the day. And just like we did before, we can type now data.head at the bottom of this part of the cell just to see what the numbers look like in our data frame after doing this. So I can run this cell, and what I can see now is our diff column still exists, but now we have numbers that are a little bit different. So 1st of June, the temperature difference between the max and min was 18 degrees Fahrenheit and 25 degrees on the 2nd of June. Then we have this NaN value here. And maybe if you've dealt with other programming languages before, this NaN is somewhat familiar. That means not a number. And this value comes up when you do math operations that don't work. So for instance, when we read in the data file, there was no maximum temperature for the day, the 3rd of June. So when you try to subtract a number from something that is not a number, the math that you come back with is not a number. So Python is basically saying you can't do anything with the column that doesn't have any data there. So this is a way of basically, when we read in the data file to indicate a missing value, and then when you try to do any kind of math using that missing value, you get back and not a number value as well. So we don't necessarily need to, for instance, create the diff column first before doing this operation. Like you could just make a new column called diff2 if you wanted. And if you do like create this diff2 column, it's not a problem at all to subtract 2 column values from one another and store them as diff2 without having to first make a column full of zeros. So there's no need to fill in and like initialize the values in a column first. So you can see here that diff2 works just perfectly fine, even though it didn't exist when doing the math to subtract these 2 columns from one another. All right, let's make another new column here. And in this new column, we can store our values from temperatures in Fahrenheit that have been converted to temperatures in Celsius. So we could, for instance, do something like data, and let's call it now temp underscore Celsius or temp C. Call it whichever one you want. And our data temp Celsius equals data temp. So we'll use the average temperature for the day values here. And when we're converting from Fahrenheit to Celsius, we have to actually put some parentheses around this and do minus 32. And then multiply the result of that by 5 over 9 or divide by 9 divided by 5. So this is just the way in which we convert from Fahrenheit values to Celsius. We had done some conversions of similar things previously. So we're subtracting 32. Just be sure to put this part in parentheses and then dividing by 9 over 5. Also good to put that in parentheses to get this to work properly. Now if we look at our output, we can see in data.head what things look like now. So if I run this, we have our columns we had before. We have diff and diff2 because I created a diff2. If you don't have that one, don't worry. And then we have temp Celsius, which is our converted daily average temperature from Fahrenheit to Celsius. Temperature of 68 degrees is 20 degrees Celsius, and of course 68.4 is then going to be something very close to 20 degrees Celsius, so it looks like this conversion worked as we would expect. Okay, now I kind of feel like the energy level in the room is a little bit low, so maybe we will go ahead and activate you with an opportunity to check your understanding, to create another column now called temp Kelvin. Got another little typo here, called temp Kelvin in the data frame. And what you can do there is convert the temperature from Celsius to temperature in kelvins. And so remember that 0 kelvins is minus 273.15 Celsius, or 0 degrees Celsius is 273.15 kelvins, as we learned back in lesson 4. So take a moment and see if you can create another column in the data frame for temp Kelvin values and convert the values from your temp Celsius to kelvins. So yeah, your task here was to basically create another column called temp kelvins, or temp Kelvin. So of course we start with our name of the column, temp Kelvin. And it was supposed to be the temperature in Celsius converted to kelvins, so we can take our values that are already in our temp Celsius column. And by the way, these don't need to be in capital letters. We're just doing that because the data file had headings in capital letters, so just for consistency. And the conversion factor in this case is that we're just going to add 273.15 to the temp Celsius values to get temperature in kelvins. After that, we can do data.head just as a quick check to see whether the values look correct. And if I run this, here's a temperature very close to 20 degrees Celsius. So 273.15 plus 20 should give us something like 293. And sure enough, there it is. It looks like our temperature conversion is working as expected. So that's the way in which we're able to add a new column and fill in values using some kind of formula as an example. All right, any questions about that? Okay, let's then take a look now at other ways in which we can select parts of our data set. So like earlier in the first part of the lesson, we selected a couple different columns and stored those in a variable called selection. But we can also select row values out of our column, and we can do this a few different ways. So one of the ways in which you can select values is to do what's called index slicing, where you basically give a range of index values and you get the values from your data frame that correspond to the index values you have listed. So if we, for instance, were to take our data frame data and put in here 0:4. The idea is that the start index and stop index will give us the values that we are looking for in this case. And actually, because of the way that the stop index works, just like the range function, we actually need to list this as 5 to get the value for index 0, 1, 2, 3, and 4. So those 5 values, we have to list here a value of 5. And if we run that as our selection, I guess we can call this selection. I don't know if we really need to, but we can basically just do it like that. And you can see that here, the output looks a bit like the head function, but this is our first 5 values of our data frame selected using the index. And so starting at 0 and going up to, but not including index 5. So that gives us 0 through 4. You can do that. It's not that common to do it in pandas because there's better ways to select things based on the index in pandas. So we'll take a look at a couple of those other examples, for instance, starting now. And our first case here would be to select values out of the temperature column for rows 1 through 5. And we're going to use that using a function called loc, or short for locator. So if we said that our selection here is equal to data dot loc. And this one's a little bit funny that it uses these square brackets instead of parentheses. So it's not quite like the functions we've been using in other cases. But the expectation here is that you would give some range of rows that you want. And then you can also list a column or list of columns that you would like to select your values from. So in this case, we're selecting rows 0 through 5 of the temp column with this selection. And if we then just do, for instance, selection, just type that there, it will print out to the screen the values we have selected. So what's different here? Well, a couple things. One, we've selected a single column. And so these are our values of temperature that are corresponding to that column. This is a pandas series in this case because we've taken only one column out of it. But you also might notice that there are now 6 rows of values compared to the 5 we had before. So when you use this data.loc function, you give a starting value and an ending value, and it includes all of them. So just be aware that this is a little bit different than the way Python lists have worked. This is a little bit different than even the other index slicing we just saw up here works. But we show you this example first because this is closest to how lists were working when we were using them earlier. And then when we use this .loc, it's going to include this end value. So we get 6 rows back now instead of 5. So that's an important difference. You can see, for example, here, the basic format for how things are working. So if we wanted to select from the temp and the temp Celsius columns, those same range of rows, we could do that as a selection equals data.loc, and then the square brackets again. We'll list which rows we want, which in this case is going to go from row 0 to row 5. And then inside of a Python list in here, we can list the columns we want. So if we want more than one, we have to put this inside of a list. So we have temp, and then we have temp underscore Celsius. The expectation for this .loc is that it will get a single selection of values or a single collection in the first space. So like before the first comma, this is supposed to be a continuous selection, and then afterwards it should also be a single variable value. And in this case, if it expects a single value, the only way to do that if you want multiple columns is to make that into a Python list. So then if we take a look at our selection, in this case, we run this, and we can see the first 6 rows of the data frame we had with temp and temp Celsius columns selected from there. So yeah, this, as you can see from the formatting as well, is also a pandas data frame. When we had selected a single column, it didn't look kind of in this nice format with the bold column headings and the alternating rows of the table, but it had this sort of more typical kind of printed out text looking formatting. Okay, time for you to check your understanding once again. And in this case, you are asked to find the mean temperature in Celsius for the last 7 days of June. And you can do this selection in this case using the row index values. So come up with your solution for how to get the mean temperature for the last 7 days of June from our data file. And once you've done that, we will continue. So the task was to come up with a value for the mean temperature for the last 7 days in the month of June. And so we can do that using our index values by doing the following. So if we were to take our, first off, our data and data.loc, that'll allow us to select the rows and things that we want. The dates or the index values for the last 7 days of June would start with index 23 and end with index 29. And if you wanted to see that, for example, well, I guess we could just demonstrate that here by doing data.tail. That's only going to give us the last 5 days, but you can see that the last index value here is indeed 29. And if we want the last 7 days, we have to go 2 days before here, so that's going to be 23. Then we were going to use our temp Celsius column. So we can then give that here. As we're only using a single column, we don't have to put this in brackets as Python lists. It's just the one column name. And so this is going to give us our selection. So that will be the last 7 rows of this single column. And then if we want the average temperature, all we do here at the end is add on the dot mean, which allows us to then take the values from this pandas series that comes from our data frame, but we're selecting just a single column, so we get our series that way. And then we take that and use the dot mean function to give us the average temperature in Celsius for the last 7 days of June, and get something like 18.25 degrees. And if we take a quick look at the temperature values at the last 5 days of June, that looks to be about right. So that's the way in which we can do things where we're selecting a column, we're selecting a range of different rows, and then also calculating something from those rows, like the average temperature. We can also use this data.loc to select a single row. So if we wanted row 5 from our data frame, that's at index number 4, we could simply do data.loc and then put in the number 4 here. If we give only a single value, the idea is that we're going to get all of the columns at this one row, in this case index 4, and you can see then here all of the column values are in the 5th row of our file, the index number 4. So here's our date, temperature, differences that we've calculated, temp Celsius and temp Kelvin, as we have seen before. So we can do things like that to select a single row. And we could then, for instance, take a single value from our individual row. So like if we go back here and just said that row equals data.loc, I can run this cell again. That's going to take that single row of values and assign that to this variable called row. And if I wanted to then figure out like what is the temperature in that row, I could just do row and then square brackets temp. And that will tell us, or tell me rather, the temperature in row 5 of this data frame. There are other ways to do this, of course, as well. There is a function called .at. And so if you want to get a single value, it can sometimes be easier to use this .at function instead. So you could say, for instance, data.at, and then you give position. So let's take the same one we had before. So we'll go index 4 and temp. So this is the name of our data frame. Our function or locator that we're using in this case is called .at. And then we have here the row and here the column. So our expectation is that it should be the same result we saw before, 51.4 degrees, because previously we had selected row 4 first, and then we took a single value out of row 4. Here we're doing both at the same time using this .at, and sure enough, we get 51.4 here. So at this point, I'm guessing this is probably starting to be a little bit confusing because it seems like there's 10 different ways you can access things in Pandas data frames. And that is the unfortunate reality. There are quite a few different ways in which you can access these values, and it can be a little bit confusing at first. We will try to stick to using this .loc approach because it's the most flexible and most consistent with how things are often done in pandas. But be aware, you may encounter examples where people are using other things like .at, or just using the index values themselves directly, or they can use this thing called .iloc. And so this is another way to select values. And in this case, I'm basically just going to say, take a look at the course page to learn a little bit about this .iloc approach. This is basically kind of more like using the index values, but you can use an index value for both the row and column, and it will ignore the column labels and things like that. To avoid confusing you further, I won't go through the examples of doing this because I think it's just going to, I mean, you're very unlikely to use this, and I think it will just be causing confusion. But it's there on the course page if you want to take a look at how to use this .iloc approach. We'll just skip that for now. So we've now gone through a few different ways in which we can select data. And now let's talk about some other things you may want to do with your data files, like filtering. So maybe you want to look at values, for instance, based on the temperature and only see certain temperature values. So let's take an example of maybe finding the temperatures in Celsius that are greater than 15 degrees from our data frame. So if we took our data temp Celsius column and just put in here greater than 15.0. This is kind of like the conditional statements we were dealing with earlier, but the difference is this is not a single value, this is a column of values. There's 30 rows of data here, and we have one condition that's being applied, and if you run this, the output you get is the index, and for each position, a true or a false for whether or not that condition is true for that date. So for the first 3 days of June, the temperature was greater than 15 degrees. Then there was maybe a week and a half when it was less than 15 degrees, a couple days when it was warmer, and eventually toward the latter half of June, finally the temperatures started to be a bit warmer and consistently above 15 degrees. So you can see that what happens here is we get a whole list of true and false row by row based on whether or not we meet this, this condition. And we can take advantage of this in selecting things from our data frame. So if we want to get the rows not based on the index values, but rather based on temperatures, we could say, for instance, warm underscore temps, make a new selection here, that's going to correspond to data.loc. And then inside here, we can put a condition. And in this case, our condition can be data temp Celsius is greater than 15.0. You don't have to put the 0.0, but I'm sort of used to doing it, so I put that there. And then we can print out warm temps to see what this data frame we get looks like. Before we do that, I'm just going to go through this to sort of explain what's going on. So you can see, of course, that we're using this locator approach to find values from a selection in our data frame. And the thing is, in this case, we're selecting the rows. If you give only one value to the .loc, it selects rows. We're going to select the rows that meet this condition, that temp Celsius is greater than 15 degrees. So we should expect to see, based on what we saw back here, that we should get the first 3 days of June, then there should be a pretty big gap, and then we should continue with more days later in the month when we take a look at what's in this warm temps variable. So if we run this, okay, here comes the data frame again. We have all the columns we had before, and you can see it starts with the first, second, and third days of June, and then jumps to the 14th of June. And so we're missing values that were here before because they fail the condition. They don't have temperatures that are greater than 15 degrees in the temp Celsius column. And sure enough, if you look in the temp Celsius column, you only see values for days when the temperature was bigger than 15 degrees. So this is kind of nice because now we have the possibility to select. If we know which rows we want to work with, we can do that. If we know the condition that should apply, like we only want to deal with temperatures that are less than 0. We want to deal with only days that are freezing and do some calculation based on that. We have the means to do that, and we can do it basically by using a conditional statement, essentially, inside, or at least using the condition part of a conditional statement, inside this .loc selector. So yeah, so that's kind of handy. And in fact, we can do even more than that if we wanted to. So if we wanted to figure out the days in the month of June in 2016 that were in the second part of the month and had temperatures greater than 15 degrees, we could do that more or less the same way that we have done before, but I'll show you there's one key difference. So let's take our warm temps again. And in this case, we're going to do data.loc like we did before. And in here, we had previously given the condition that our temperature in Celsius had to be greater than 15 degrees, and we'll actually do that same thing here. However, let's put some parentheses around this first. So we'll do data and then our temp Celsius in quotation marks greater than 15.0. But we have another condition here. So this is going to give us all the days in June when the temperature is bigger than 15. But we also only want to have our data for the second half of the month. So that's why we put parentheses here, because now we're going to do this ampersand, or the and character. And in parentheses here, we're going to have a second condition. Strictly speaking, I again don't think it is required in the syntax that you have these parentheses, but I just find it easier to read if you put your conditions inside parentheses. So that's why we're doing it like this. So we had our requirement that the temperature be greater than 15 degrees, and also the second half of the month, which means that our data, and this is going to be the lovely year mode column, because that's why we have our date right now. The values in that column should be greater than or equal to 2016 for the year, 06 for the month, and 15 for the day. So this will give us the days in June that are at least the 15th of June. So that's how we're going to get the second half of the month in this case. What we haven't really seen previously in the earlier lessons, and I do appreciate this is getting a little bit complicated, is the use of this ampersand character. Why do we use that instead of the word and? I would think maybe some of you might be asking yourselves that question, because we learned to use and earlier when we had two different conditions. The reason for this is that what we have when we're doing and applying these conditions in this case is that this is returning a whole column of true and false values, not a single true or false value like we had earlier. This is also returning a whole column of true and false values for the rows that meet this condition. If you want to have two different columns of, or like lists of true and false values, and compare which ones are going to be true row by row, you have to do that using this ampersand character. The same thing is true if you want to have an or condition, that instead of the word or, you would put this vertical bar character. So this, if we scroll back up for just a second to where we were when we first did this thing where we said temp Celsius greater than 15 degrees, you got true, 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 false, 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 whatever. Essentially, if we want to go row by row and compare those things, we need to use this ampersand character, because that will go to the first row and say, okay, is it true here and true there? Then yes, it will be true for the first row in our selection. So we will again get some opportunities to work with this in the exercise, so don't worry right now if this isn't totally clear. I do appreciate that this is getting a little bit more complicated, but let's see now that we have this big nasty thing typed in here. What do we get when we run this? So it's just as a reminder, we're selecting temperatures above 15 and dates from the 15th of June onward. So do we pass our tests? Well, first off, it looks like our dates are starting from 15th of June, so that looks good because it was true earlier that the 1st, 2nd, and 3rd of June had temperatures greater than 15 degrees. So those values have been excluded by the condition that it should be at least the 15th of June. And in addition, our temperatures in Celsius all appear to be temperatures bigger than 15, so it looks like things are working properly. You might notice here that we have this index value that still refers to the original rows that were there, and we have a different data frame called warm temps in this case. It is possible to reset the index if you want, to get rid of the reference to the earlier rows. You can do that using this reset index option. And so, if we wanted to, we could basically just do the same thing that we have done before. So if we take our warm temps, we could say warm temps dot reset index. And then here, what we want to do is say drop equals true. If you don't include the drop equals true, it will keep the old index value as like a separate column in your data frame. So depending on what you're doing, you may or may not want to do that. But the reset index will start things so that the first row now starts at 0 and it goes 1, 2, 3, 4, and so on from there. So if we take a look at our warm temps after doing this, with our reset index drop equals true, there is no additional column here, but you can see now the index values start at 0. So sometimes, if you're reading in a data file and you're kind of cleaning away data you're not going to use, you may want to basically just drop out a bunch of rows and then reset the index to be able to select things like, every 10 values you calculate something, and you could then use the index selection more intuitively like this. Okay. I'm going to skip this check your understanding at this point just because I think there's a few things I want to still show you from today's lesson that'll be relevant for the exercise, and we still have some time, but yeah, we'll skip that one this time. If you want to, you can go ahead and do the check your understanding yourself when you have a moment. But let's tackle a couple other common issues we have to deal with, one of them being missing data. Very often the case when you're dealing with real-world data sets that there may be days of missing data, there might be months, there might be years of missing data. There are global situations that happen like wars, and when those things occur, sometimes the top priority is not to make sure that the weather recordings for every day are stored, but rather that people prioritize other things, and as a result, you'll see occasionally, especially in European data sets, periods of time when data is missing that seems to correspond with major global events. So dealing with this missing data is a common thing that you're going to do. It's probably one of the first steps you would have in any kind of workflow you would have for dealing with data files. So we have basically some different columns that we're dealing with where we have already missing values. I don't think we made the diff min column. I must have missed that. But we have these other columns like diff, and you noticed in our diff column from before that we had these NaN values in there for not a number. And oftentimes you don't want to deal with those values because if you're missing the data from that day, perhaps it's not meaningful for your analysis. So we're going to drop our no data values based on the min column, but let's just take a quick look at what our data frame looks like at this point, just by typing data here. So here's all of our columns. And you can see, for instance, here in the min column, if we scroll down, that later in the part of June, toward the end of the month, there's a couple days when we have missing data values. And so what we're going to do first is just drop out our rows, like you can see index 26 and index 28. We can drop those because they're missing data. And so the way in which we can drop our data in this case is, let's say maybe we can use our warm temps data frame. Let's take a look at that one actually first, because I think warm temps is going to be nicer for us to work with. Same problem, that these 2 days toward the end of the month of June are missing data. So row 9 and row 11, we can take care of getting rid of those by using a method here where we say warm temps clean. Make a new data frame that we can call warm temps clean, where we've dropped away our missing data values. It's going to be equal to warm temps dot drop NA. So NaN is not a number. Drop NA drops out the missing values. And in this case, we'll say our subset equals min. So you could list multiple columns here for your subset. We're just going to list a single column to indicate that we want to drop out any row that, any row in the column called min that has an NA value. If you want to drop out all of the missing data, you could leave out this subset parameter, and that would drop any row that has a missing value in it, but you don't always want to do that. So it's nice to know how to do this, where you drop row values only from certain rows that are missing. And so then we could say warm temps clean to see what we have in that cleaned up data frame. And if I run that one, after dropping the missing values, or any row that has a missing value in the min column, you can see now that our value at index 9 and our value at index 11 have disappeared, because in the min column they had missing data before. And now we have a clean data set we can work with. There's no missing values here, so we could proceed to analyze our climate data further if we felt like we wanted to do that as an example. On the course page, you can find another example of how to drop values in place, which will just modify the data frame you're working with, rather than having to, like we did up here. We had warm temps clean equals warm temps dot blah blah blah. If you wanted to drop them out of the data frame without renaming it, you could add this in place equals true, and then it, as it says on the course page, gives you a little bit shorter syntax to do that kind of common operation. But I'm not going to demonstrate that for the sake of time today. So we saw an example of how to drop the missing values. We can also fill in missing values, and depending on the situation that you're dealing with, you may want to do this. So like in our warm temps data frame, we still have the missing values there. This is not warm temps clean, but just warm temps. So if we take a look at that one, we can see that, yes, there's still missing values here in index 9 and index 11, like we had before. And if we wanted to do warm temps.fill NA, we could basically put in some number instead to indicate a missing value. So instead of having it be not a number, as it is here, we could do warm temps.fill NA minus 9999. This is just some arbitrary number, but for those who've used like ArcGIS before, sometimes it will identify missing values by the value minus 9999. And if you run this, the output that you would get here in this case, you can see now would have the missing NA values filled in with minus 9999. So you can do things that way. I don't think it's a very good idea, to be perfectly honest, but just so that you're aware that it's possible to do, we show you that example. The reason you want to be careful with doing this is that if you fill in missing data values with some number, and then you do something like calculate the average of the values in some column, that number will be included in the average you calculate. So if you calculated, for instance, the average temperature well, let's take the average minimum temperature in our warm temps column. So if we took warm temps, and let's just take our min column by itself, we could fill in the NA values like this, just for a single column, by adding in this thing here. And if we did that and then did dot mean, and I'm just doing this to demonstrate the problem, you get a mean temperature of minus 1,491, which physically has really no meaning. So when you fill in values here, you really want to be careful that like you have a good reason to fill it in and not just to simply drop the values, because if you were to drop them, I think you probably would get better results. The mean temperature you should be getting is something like 55 degrees, but because of these filled in values, you get some erroneous mean temperature. So be careful with that. Probably the only good reason to do that is if you have some GIS software or something that will identify certain number as missing data and not plot the value, for example. Okay, a couple other things, and then we'll take a look at the exercise. And I can kind of tell you guys are getting fatigued, so I don't know. Kind of gear yourself up mentally for 5 more minutes of attention, and then we're just about done. These things are sort of quite relevant for the exercise this week, so I do want to demonstrate them. Otherwise, I would just say like we could be done now, but I think it's good that you see this stuff because it will come up in the exercise. So just like with other data formats, we can convert values from one data type to another in pandas. So we converted, floating point numbers to integers to strings and things like that in some of the earlier lessons. We can do the same thing in pandas using a method called .asType. We'll talk about this warning here in just a second. But let me maybe before we do that, I'm just going to put an extra cell here. And if we did something like data, let's take our, how about date? So we'll do year, mode. We could do that .asType. And then in here we could say float. So this is going to take our values in the year mode column of our data frame, convert them to floating point numbers. They're integers as they're stored right now, but we can just demonstrate how this works by doing data year mode .asType float. And you can see now that all the numbers we had before now have this .0 after them. I think we could also convert them to strings as str if you wanted to, and I'm just demonstrating this so you can see how it works. So this might not look any different in the output because you see the numbers look the same as they did when they were integers. However, the data type now says object, which is the pandas data type to indicate that you have a character string for the data that's in this column. So, so the converting things from one type to another, you just do the .asType, and then you give some data type you want to convert to. The little warning in the text here is that you have to be a little bit careful with certain types of conversions. Going from an integer to a floating point number, no problem. Going from an integer to a string, no problem. But when you go from a floating point number that has a decimal place to an integer, if you just convert it directly, what happens is that everything after the decimal place just gets dropped. So the number 99.99 would just get rounded to 99.0, or well, 99 is a whole number. So as you can see the example here, instead of being rounded up to 100, it just gets truncated to 99. So if we take, for instance, our original values here in our temp column, if we look at those, we had whatever, 65.5, 65.8. And if we said, like, let's just take those same values, just going to copy paste this, and we did .as type int. What happens here when you run this is that everything to the right of the decimal place just gets dropped. So you see that the temperature here is 65 instead of what you might expect it to be, 66. 65.8 just gets reported as 65. And so you can see clearly the problem here is that it's not rounding things, it's simply dropping everything after the decimal place. Of course, we can round the values. So if I take our data temp.head, we could do .round. And if we round it to having 0 decimal places, that will round it to being a whole number. And then after that, we can do .as type int. So what this does is it takes the data from this column. We use .head to get only the first 5 values. We use .round to round those values to have 0 decimal places, and then can convert them to integers. It might seem a little bit clumsy to do things like this, but if you do that, what you'll see is that our values now are rounded up to 66 instead of just being truncated as 65 as they were earlier. So it really depends on whether that you need that precision, but to handle things properly, it's nice to do .round anytime you're converting a floating point number to an integer. All right. There's something here about the unique values, but I think maybe we can skip this. All it would really do is just tell you how many unique values are in a column of your data frame. So how many unique temperatures you have there, for example. I think we can skip over this for right now because it's not that important, and you can see how to do it on the course webpage. What's maybe more important is how to sort files or sort values and how to write things to a file. So if we wanted to sort our data frame based on the temp column, we can sort things in ascending, so meaning that the values are getting larger. And we could say, for instance, data.sort values, sort underscore values, and then by equals and temp. So this is basically just asking us, how do you want to sort them? Well, we're going to say you can sort them by the values that are in the column called temp. And so if you do this and run it, what we should expect to see is that our temperatures, or that our rows of our data frame are now presented in order of increasing temperature. So here's our temp column. Lowest value is 49.4, and then it's going up from there. So things are no longer sorted by the date, but they are now sorted by this column, and just scrolling through the values we have here, it looks to be correct in this case. If we just copy this here just for the purposes of demonstration, scroll down to our next box. If we want to have things that are in descending order, so starting with the biggest value and going down from there, the way to do that is to add a parameter here called ascending and set that equal to false. Not flats, but false. Otherwise, it's assumed that you want to sort things in increasing order, but if you say ascending equals false and run this, you then get the same output, but in reversed order. So now going down in terms of temperatures from the maximum to the minimum in the order of the values that are listed there. Okay, so we have done a whole bunch of pandas stuff at this point, and perhaps have reached the stage where after you've done all your data analysis, you want to write out your output to a data file. It's not particularly difficult to do this. We could start by maybe defining a variable here called output underscore FP, which we'll use for our output file path. And we'll give a file name here. And we could call our file cumpula underscore temps underscore June 2016 or something like that, dot CSV. So we're going to write our file out in a comma separated value format because we'll use this pandas function called toCSV. So it doesn't matter if your file name is exactly the same as this, it just has to end in .csv just to make it be clear that you have a comma separated value format. Writing the file out itself is as simple as writing data.to underscore CSV and then output underscore FP. That's the file name we're going to write to. And we'll, in this case, include that sep equals comma. So this is just going to indicate we want to separate the values with a comma. I don't actually think you even need to include that. I think it just assumes a comma, but we'll put that in here just to be perfectly clear. And if we run this cell, you won't see anything. But if we go to our file browser over here, there is now a new data file here. And I guess I would have to kind of slide this thing over to see that that's our CSV file that we've just saved. And if I double click on it, I get a preview of what has been written out to this file. And so I can scroll through here and take a look. And I see things look, more or less like our data frame that we've been working with. Here's our index. We've got our columns that are all labeled. And everything looks okay there. Except this is kind of ugly in the format that's been written out because there's a lot of values after the decimal place. Typically, when you write out a data file, it's kind of nice to have the data file look rather consistent in the number of decimal places that are given after a value that's in the data file. And we can address that issue with one small modification. So let's copy what we have here. We had already set our file name. Okay, let's grab this thing too. And so I've just copied the stuff down from what we had earlier. And we could say output FP2. Let's call this cumpula temps above 15 June 2016.csv. So slight modification to the file name. Then what we can write out here is actually our warm temps .toCSV. We'll have now output FP2. Separator can still be the comma. Let's ignore the index in this case. We don't need to have that column with just like the index values in it, so we can add index equals false, and then finally float underscore format equals. And then there's this kind of confusing %.1f. What this is going to do is, and I've misspelled above, so I'll fix that. We're going to write out our file here with our output FP2 file name, separated by commas. We're not going to write the index column out. We had that before, but it's really not very useful, so we'll not include that one. And then all the floating point values will be formatted here with one decimal place. So that's what this %.1 indicates. It's any floating point number will be written with one decimal place of precision, and that's that. So if I run the code now, I get another data file. I can't tell which one is which, so I've got there's the above 15 CSV file. So let's open that one up. And now you can see we don't have an index column anymore. And if we scroll over to the side, not to see Twitter crap, but instead to see our columns that we have here, you can now see that our values are rounded to a single decimal point of precision. So that all looks to be working properly, nicely formatted output file that we can deal with at some later time, because now we've written what we've done out to file in such a way that we can work with it in the future if we want to. That's it for the lesson for today. We should take a quick look at the exercise just so you know what's going on with that, and then I think we'll be done. But before we go to the exercise, do you have any questions at this stage? I do realize there was a lot of new stuff introduced today, so I feel like every year this lesson is kind of a heavy one, and we've tried to reduce it a little bit, but it's a bit hard to draw the boundaries for what should and shouldn't be included here when introducing pandas. So any questions or problems you've encountered? I can maybe make this visible if you're wanting to see what was on the screen. Okay, let's have a quick look at the exercise for today. That is somewhere here. I think it'll go like this, exercise number 5. Make this bigger so you can see it. Okay, exercise number 5, we're basically doing our first data analysis using pandas, no surprise there. And there's 3 questions, or 3 problems, I think. Our input data is, again, some of this climate data from the National Oceanographic and Atmospheric Administration webpage. You could find the data file if you want to look, linked from the description of the exercise, and of course it's in the repository you'll be working with. It looks like this, so you can see already that we're dealing with a little bit different data format than we had before. There'll be some challenges that come along with that. And then we have our 3 problems that are graded and 1 extra problem. So let's see what those look like and what you'll be doing for those problems. Problem number 1 is basically just to explore the data set a little bit. So your first task will be to read this data file in. And when reading in the data file, you're going to have to handle one tricky element to it, and that is that there's different numbers of these star symbols filling in missing data values rather than simply being empty. So you're given a tip for how to handle that when reading in the file. But that's the first thing you'll do, read in the new data file in a format that we have not dealt with yet. Then you have a few questions here, like how many rows, what are the column names, what are the data types that are in the columns. So this is kind of stuff that we handled in today's lesson. And so you'll fill in those values, and then we have a question here about the average temperature in Fahrenheit in the temp column, what the sort of standard deviation is in the max column, and then how many unique stations exist in the station count. So this is the one thing where you may have to refer back to today's lesson to see how to do this .unique, or how to use the .unique method. But don't worry, it's not very difficult to use. So you should be able to, I think, just take a quick look and find that. That's more or less what problem 1 is. It's essentially just to get some experience loading in a data file and doing some basic exploration of the data set. Problem number 2 didn't load properly, so we'll need to refresh. In this problem, we're dealing with a bit of manipulating data, selecting values, and things like that. So here we have first to read in another data file, similar to what we were doing earlier, same data. So basically, you're able to read it in the same way. And you can then check out to make sure the data frame looks okay. Then we're going to take only a subset of the data that's been read in from certain columns that are listed here and store those in a variable called selected. So you'll do that. Then you can drop out any rows that contain missing data from the temp column. Again, kind of like what we did in today's lesson. After that, you'll get to create a new column where we convert the temperature from Fahrenheit to temperature in Celsius. So you have an equation for how to do that. And then you're going to round the values to have 0 decimal places, and then convert the values into integers from floating point numbers. So again, you get to practice using some of these different methods for rounding and data conversion or data type conversion. Then we're going to split this data frame into 2 separate data frames, one called Kumpula and one called Rovaniemi. And that's because we have data from 2 different locations in the same data file, and we can use this USAF code to split things like that. So you do that, and then you write your files, or write your data out to files. Yeah, that's basically it for that problem. So in the end, you'll have data for Kumpula, you'll have data for Rovaniemi, and it will be cleaned up and ready to use for the next part of this problem number 3. So at this point, we've got Kumpula data, we've got Rovaniemi data, and we are ready to do some analysis of the data. What's your job to do at this stage is to calculate some median temperatures for the summer. So first we read in the data files, get more practice doing that. And once you've read them in, you're going to find median temperatures for Kumpula and for Rovaniemi for the summer months from the data file that you're given. And then we are going to go through and deal with things like individual months. So we may select the month of May and June and things like that. So we're going to assign values for Kumpula for just the month of May and just the month of June, and same for Rovaniemi. And we're just selecting from our data frame then those values. And finally, at this point, we can then use the print function to print out the maximum and minimum Celsius temperatures for both places in the months of May and in the month of June. And then you're asked a couple questions here about like whether Kumpula is a much warmer place than Rovaniemi for the months that we're looking at. So it's all about reading in data files, selecting values from the data files, and doing some kind of analysis to give you some information from the data that we're working with. I don't recall quite how big the data files are, but they're bigger than we were dealing with in the exercise today. So there's good reason to take this approach rather than just going into doing things in Excel. And for those of you that are interested, there is a problem number 4 about parsing daily temperatures. What we have in the data set that we're dealing with in our data file are multiple temperature observations per day. And what you want to do is basically aggregate the data to take these multiple observations of temperature per day and make them be temperature values for one time per day, or basically combine multiple measurements into a single temperature value for each day. We did not cover how to do this. We'll deal with it next week, but if you're looking for something extra to do for fun or entertainment or whatever, that's what the problem number 4 is all about. Any questions at this point? I know we're like past our time, and I can very easily tell you're sick of this at this point. So I don't blame you. It's a long lesson for me too today. And if you don't have any questions, my advice this week is it may be beneficial to you to go to the exercise help sessions on Thursday and Friday. The exercise today or this week is a little bit more demanding than some of the earlier ones, and just be aware you might need a little extra help to finish this one. So please do that. Ask questions in Slack if you have them, and we'll see you next week.